Now we will have the last segment of today's seminar, that is the student flash talks. So first we have Mehdi. He's a third-year PhD student at the ORC, working with Rahul Mazumdar. And in this talk, he will present work on a sparse plus low rank compression framework for large language models, aimed at improving efficiency while preserving performance. So please, let's welcome Mehdi, and the floor is yours.
Thank you for the introduction. Today I will present 3-base-all. This is a paper that has been accepted to the recent NeurIPS 25. It's called an algorithmic framework for sparse plus low-rank compression of LLMs. It's a joint work at the Operations Research Center with me, Mehdi Maqni, Xiang Meng, and Rahul Mazumdar, who's my advisor. So I think in this talk, I would like to show how operations research or optimization generally can help generative AI tools, or like LLMs in this case, in a certain area, which is model compression. And what model compression means is trying to minimize a certain loss function compared to the LLM under some constraints under the model weights. So for example, we might want to have pruning, so sparse weights. We want to have zeros in our LLM weights. Quantization means we store the LLM pre-trained weights in low precision. We might want to refactor the pre-trained LLM weights into low rank factors, or combinations thereof. And this paper is about sparse plus low rank compression of LLMs. And so later on, I will try to motivate this compression from a CS/LLM perspective, from a hardware perspective, because there have been developed some specialized CUDA kernels that allow for inference speedups and memory reduction if you satisfy certain constraints on the model weights. So this slow paper is a reference. For example, if you have 2 to 4 sparsity, this is a specialized type of sparsity plus 112 rank configuration, then you can get up to 1.53x speedup and 0.63x memory reduction compared to the dense model. Prior work also, like OATS, has demonstrated that sparse plus low rank can be a good alternative to pure pruning in terms of retaining the model performance under the same compression rate. And what compression rate here means is the number of non-zero elements that you store compared to the pre-trained model. Sparse plus low rank is also LoRa aware. LoRa is a parameter efficient fine-tuning method. What it does is it fixes pre-trained weights, and it fine-tunes low rank components. And what we mean here by LoRa aware, it means that once we have, for example, a sparse plus low rank decomposition, we can fix the sparse components and only fine-tune the low rank components. So they act as a smart initialization for the low rank fine-tuning. And so in the literature of model compression, there is this layer-wise reconstruction error, which means you have your pre-trained weights. You look at them as a bunch of matrices, and you want to match the outputs of these matrices. So here, for example, we have W hat, a certain layer in your LLM. So you look at your LLM as a bunch of transformers, and then the transformer as many layers, linear layers. And you want to match the outputs. X is the input activations to this layer. And you want to match the outputs of this layer with its sparse plus low rank decomposition. And this one is a regularization term, which means we try to match the output, but we don't want the actual weights themselves to deviate a lot. Here, S is a sparsity set. It could be your regular unstructured sparsity. So for example, you want 50% of the weights to be non-zeros, or it can have more combinatorial constraints. N to M sparsity, it means for each m consecutive elements, at most n of them are non-zeros. So we will try to develop certain algorithms that accommodate any type of sparsity set here. And we have the low rank constraint on L. And under this framework, basically, we go from a computer science or generative AI problem where we want to compress models and serve them at large, to this optimization formulation, which is kind of familiar with in the optimization realm. Notice that it's also kind of related to robust PCA. Robust PCA is a statistical problem where we want to decompose a certain matrix or model weights into sparse plus low rank decomposition. And the main difference here is that in robust PCA, there is no sensing matrix X. So a lot of the algorithms that have been developed for robust PCA cannot really be applied directly to our problem, but it falls under the same literature. So what we're trying to design here is a method to solve the introduced optimization problem from earlier. And we have found that ADMM, alternating direction method of multipliers, is a very suitable method to approach it. And so one way to do it is we rewrite the problem in this way. We create a copy of the sparse weight S, and we're going to enforce sparsity on the block component D, and let S be unconstrained in our optimization. And once we write the augmented Lagrangian, we have a block coordinate descent type of method. And what's nice about it is all of them can be computed in closed form and efficiently. So the first one is the quadratic minimization. Because there's no constraint here on S, it's really easy to get the closed form solution in this way. And in the paper, we show also some numerical linear algebra tricks to do this efficiently. Also, to accelerate convergence, we use like an adaptive rho T here throughout iterations. And there are certain techniques that allow you to do this pretty efficiently that are clearly presented in the paper. The second block is the low rank constraint. And this is an interesting problem that has appeared in the 70s in the literature of reduced rank regression. And basically this problem where you have a sensing matrix and a difference of weights, it's some sort of truncated SVD with some reweighting matrix H that you introduce here. And finally, the third block is a hard thresholding component where you want to project your weights on the sparsity sets. So here, this is a simple magnitude pruning. For example, if the constraint is 50% of sparsity, it means you leave the largest 50% of weights intact and you threshold the other ones to 0. If you have some combinatorial constraint, then it's also similar. You look at m consecutive weights, you leave the largest n, and the other ones are set to 0. So this is the OR tools kind of approach to this problem, where we have the 3 block updates to solve the introduced problem here. But also there's a computer science perspective to it. The loss we have introduced is localized, which means we only look at layers locally. Each layer is basically decomposed into sparse and low rank at a layer level. And then another question is, can we have another loss that is closer to the LLM entire loss and which we can actually optimize? And one way to do that is transformer matching, which we introduce here. What transformer matching tries to do is basically use the 3 block ADMM approach to find a support plus low rank decomposition for the weights. And now, because you have the high quality support, you can fix it and then try to match the Frobenius norm of the outputs at the transformer level. So now here, this is no longer convex optimization. One needs to do gradient descent type of methods to optimize this. This is also a universal approach in the sense that transformer matching doesn't only enhance our method performance, but also any sparse, like pure pruning, or sparse plus low rank decomposition. And here we show some examples. OATS, hassle-free sparse GPT, and hassle-free ALPS are 3 different methods that try to decompose the model weight into sparse plus low rank decomposition. And then we show that transformer matching can optimize certain loss functions. For example, here, wiki text to perplexity. And so basically, transformer matching is universal throughout different algorithms. Here, the dot, or like the circles that are not full, are the methods without transformer matching. And we can see that our method, 3-basal, runs in 4 hours, much faster than other competing methods, 15 hours for the second best, 6 hours and 8 hours. And this is because doing a good optimization can actually help over heuristic-based methods in this field. Transformer matching adds a certain number of hours for the compression. So here, it basically adds a constant 3.5 hours roughly time to improve the performance. And these are the results for 2 different models. The first one is a llama 3.8 billion, and the second one is llama 3.23 billion model. For our 3-block ADMM, we also have some convergence results that basically guarantee that the number of iterates are going to converge to a final solution, W bar, under some constraints on the step sizes, etc. And so finally, one question that remains in model compression is, if you have a localized loss, maybe you can do something better in terms of objectives. So here, what we're looking at is the Frobenius norm between the outputs, the difference in outputs between the pre-trained model and the compressed model. And we see that lower here is better. And our method, 3-basal, can do better performance compared to other competing methods on, for example, here, attention query projection and other attention linear layers. But then another question after this is, if you do a better job in the localized loss, does it actually propagate to the entire LLM loss function? So if you compress a model well locally, is it going to have a better performance in, for example, perplexity tasks? And this is what we can see in these figures. So here, for example, under different compression constraints, the ones to the left are most aggressive. So here, this corresponds to roughly 25% sparsity plus 64 rank configuration. C4 perplexity is the loss function, and lower is better. And we see that 3-basal, our introduced method, gives a better performance, especially when it's enhanced with the transformer matching. Similarly here, this is C4 perplexity, so lower is better. And we compare 2 different things, compression before LoRa fine-tuning, which are the boxes to the left, and compression post LoRa fine-tuning, which are the boxes to the right here. And we see that, for example, before LoRa fine-tuning, we can achieve up to 35% reduction in the gap to dense model. So this is the pre-trained llama 3.21 billion model, perplexity on the C4 dataset. We also have here, for example, runtimes on H180 gigabyte GPU. And the LoRa fine-tuning takes roughly 0.7 hours for this model under 15 million tokens. This is the QR code for our paper, and this is the code URL. And I'm happy to take any questions.
Go ahead.
So related to your data, so X was your data, right?
Yes.
Are you using here like the entire data that you use to train the model, or you have to take a subset of it to make things scalable?
It's a subset. So we use 128 segments. Each one has 4,096 tokens.
Okay, yeah.
And then it's actually basically reshaped to become 2D problem. So here, X is basically 128 times 4,096 is the length. So it's a huge stall matrix, actually. And this introduces a lot of problems in the optimization, because some of the older methods that have been designed for robust PCA, you cannot really scale for sensing matrices that are this tall. But we have to deal with that as well. It's a very tall matrix by the hidden dimension, which is 4,096. And that's more manageable.
Okay, I see. Thanks. So,
Very quick question. Do you that if you compress LMs, maybe it's easier for you to identify which ways to remove to be able to machine learn some training data? I don't know.
For machine learning, you said?
Yeah.
Actually, it's not a field that I'm used to, so it's actually possible. So what we've seen here is, for example, if you try to compress a model on, let's say, wiki text data, then we can have really good performance on adjacent data sets. What it means is like text that has the format of wiki text data, for example. But with this compression and optimization formulation, we lose a lot of the performance, for example, on math tasks, or like Spanish or things like that. So this is also like makes the model a bit more specialized to the data we're using. Yeah, corresponding to machine and learning, I don't have a solution, like an answer for that.
Okay, thank you, Mehdi.
Thanks.
Josh is currently a second-year PhD student at the ORC. He's working with Alex Sakia, and in this talk, he will present work on designing and evaluating LLM-based agents for interactive optimization using a conversation-based framework. So please, let's welcome Josh.
Thank you, Felipe. So I actually think this talk is kind of a nice culmination of a lot of the things that we discussed today, in particular over the last few hours, talking about having AI agents talk to each other, and then from earlier today we saw some other examples of using LLMs for interactive optimization. So I think it can kind of tie everything together in a pretty nice way. So really quickly just want to call out both of my collaborators here. So of course my advisor, Alex, but then I've also received invaluable guidance from Sebastian Martin, who's an associate professor at Northwestern's Kellogg School of Management. So just to briefly talk about interactive optimization and frame the conversation, and I know this is something we've talked about a number of times today, but I know some of you came in later and maybe didn't hear some of those earlier discussions. So really the challenge that we're addressing through this work is the fact that decision makers often, they know their decision problem very well. They're the ones who do all the consensus gathering among stakeholders, but they don't necessarily know how to use optimization algorithms and models to solve their problem. So they will bring in researchers and engineers, and these may be from within a different department within the same company, or maybe there's some third party, someone from academia, and they'll bring these experts in to help them model and solve their problem. But what's often the case is that the first iteration of the model is not exactly what the decision maker is looking for, because there's a lot of details that aren't necessarily obvious for a decision maker to provide up front. So they provide some feedback, and this process can go on many times, and it's very time consuming when you have this sort of direct interaction between a decision maker and a researcher or an engineer. So what's often the case is people will build these interactive decision support tools that sort of allow or enable decision makers to provide their first order feedback to these tools as sort of an intermediary between the decision maker and the researcher. And often these tools can be made with things like Excel, where you can impose a constraint and then it'll filter down on a subset of pre-computed solutions or something like that. But with the sort of the rise of AI agents, we can sort of redefine how we think about interactive optimization using these LLM agents to sort of facilitate this interactive optimization in a much more dynamic and flexible way. And so one of the things that we do in this paper is we look at using LLMs for interactive optimization, but we take a little bit of a different approach from some of the other works that I think have presented today, in that we sort of take a step back and we think more closely about how the LLM agent is actually interacting with the optimization model. So we don't just assume that this is going to be done through writing arbitrary code. We actually want to think about, is there a way to do this that makes this interaction very reliable, very interpretable, and very predictable. And so what I have here is just what we sort of term as an optimization agent, which is this idea of providing an LLM with a set of tools that allows it to make these really targeted adjustments to an existing formulation. And this toolkit here, this is really just supposed to be illustrative. It's not necessarily the exact optimization agent we use in this work, but the idea is you can provide it with a toolkit that allows it to make these really targeted adjustments, like adding or removing constraints, modifying objectives, things of that nature, where you're not letting necessarily just write code to do these things, but you can have it call a tool and have it make these adjustments in a very deterministic way, so you know exactly what it's going to do. And then there's of course other benefits. So you can guarantee correct linearization procedures if you want to, if you care about the exact formulation. So you want to make sure you have a good formulation. You don't want it to write bad or loose constraints that might result in a very poor model. Things of that nature. So to that effect, I just wanted to provide here sort of an illustrative conversation to help motivate what I'll be talking about in the rest of the talk today. So this actually comes from a case study a little bit later in the talk, where we're looking at a school scheduling example. And in this case, this is a principal who is seeking help with a school scheduling problem, where, and I'll get into the details of the case study a little bit later, but the main idea here is that they're seeking help with this decision problem, and they're approaching this optimization agent, and they're providing some feedback about this initial solution that they're unhappy with. And so the idea here is that this optimization agent can take this feedback and make some targeted adjustments to the model. In this case, discussing the changes that were made, how that affected the objectives, the trade-offs that are reflected by those changes. And then the decision maker can then react to those changes, say what they like and what they don't like. And this process can continue for potentially many turns until ideally you reach a solution that the decision maker is happy with. And they walk away very satisfied as a result of this interaction. And they didn't, at no point did they ever need to have any understanding of the sort of the optimization model that's underlying this interaction. So this introduces some pretty interesting research questions, namely, how should we design a conversational chatbot for optimization? So we've seen a number of architectures today that were discussed today. OptiGuide, we have this more simplistic sort of architecture we introduce here. So we sort of ask this question of how should we think about how to design these things? And how do we, and then sort of a very related question here is, do tools support a targeted exploration in a way that in some sense leaves users more satisfied? And then we want to know how to systematically answer that first question. So this work is largely focused on this question of how to actually evaluate these agents at scale in a way that's very, very rigorous and verifiable. And so digging into this second point a little bit, what we often see in the literature is a one-shot question and answer style of evaluation where you have some ground truth. So you'll see these data sets where you'll have very well-specified questions that are like, what if the cost of this thing goes up by 10%? Or in auto-formulation data sets, you'll provide these natural language description of a problem, and they're very well written. They're not written in the way that a decision maker would really think about these problems, because a decision maker doesn't really know how to parameterize an optimization model or a formulation. So they're not actually going to know all the information that they need to provide, and so it doesn't really reflect these real interactions. And another reason for that is that in reality, this is going to be a sustained multi-turn dialogue. So you can think of it as a conversation, right? And that's often not the case in what you see with how evaluation is done in the literature. So an intuition you might have to address that is to have humans interact with an optimization agent on sort of a human-based study. And that's actually something that Connor discussed in his talk, where they did, I think it was like a 10-person diary study. The challenge there, though, is that this can be costly. It's not really repeatable. It doesn't really allow for decentralized research. And so what we propose in this work is to actually have an AI play the part of a human with external scoring based on verifiable and rigorous criteria. And so to illustrate exactly what's going on here, essentially what we're saying is we have our optimization agent now interacting with a data set of what we call decision agents. And these are AI that are large language models that are playing the part of a human. And we're scoring these conversations based on verifiable and rigorous criteria. And what I mean by that is that we're not just taking these conversations, passing the transcripts to another language model and using LLM as a judge to score them that way. We're actually designing the decision agents in such a way that we can actually have a very verifiable scoring mechanism for these conversations. So the advantages of doing this is that it's very repeatable and scalable. You can leverage the strength of large language models, and that's because they're very good at conversation and sort of behaving like people. It can really only get better as AI improves, because that means AI is going to get better at playing people. And it's very flexible, so you can really tailor these decision agents to your specific decision problem to create a number of different benchmarks. You can capture a wide range of different types of people by parameterizing them in a very carefully constructed way. But of course, there are challenges associated with this approach as well, namely the fact that if we want verifiable and rigorous criteria, that's necessarily going to exclude some real-world use cases. So to that point, essentially what we're saying here in this setup is that the goal of a decision agent is to choose a solution for a specific decision problem. So we're assuming that there's some decision problem, they have a space of decisions that they're trying to choose over, and the goal of interacting with the optimization agent is to help them arrive at a good decision. And so this introduces a set of questions of its own, namely, how does a decision agent decide whether a solution is good or bad, and then how does it communicate that feedback? So to answer those, we introduce these are two very high-level parameters, and essentially there's a lot more detail to these, but I'm just trying to convey the main idea here, which is that we have a utility function, which is supposed to mimic human decision-making. So you can imagine humans, when they look at a solution and they're thinking, and you're thinking about how you feel about it, you have some sort of internal, inarticulable utility function that you're using to evaluate that solution, whether or not, maybe you realize that. So this provides us with a very nice verifiable goal to evaluate our decision agents because they're trying to maximize this utility function. And this is going to drive the content of their feedback. So they'll say, it'll essentially inform what sorts of things they're going to ask for when they're interacting with the optimization agent, but it won't necessarily determine how that request or that feedback is conveyed. And that's controlled more by this role-playing background. And once again, this is just sort of an illustrative example. The real prompt is much more complicated than this, but this conveys the main idea, which is that it'll say something like, you're a stressed out superintendent under cost-cutting pressure, you don't know much about optimization and struggle to explain what you want in terms of precise objectives and constraints. And so the idea here is we can capture a very broad range of human behaviors, the way different types of people think and the way they communicate. So like two people who maybe they want the same thing in the solution that they're looking for, but they communicate those ideas in very different ways, right? And so that's the sort of thing we're trying to capture in this evaluation framework. And so taking this idea of a decision agent, we can construct a benchmark data set of decision agents. And then for an optimization agent, we can define a score, which is just the average normalized utility across all of these interactions with our decision agents. And then we can also alternatively define a success-based metric, which just sort of tracks the fraction of conversations that reach this utility maximizing outcome. And one nice thing about scoring it in this way is that we're not just looking at the scoring value at least gives us some informative mechanism to tell us how far we were from reaching a utility maximizing outcome. So it's not just this binary 1 or 0, we were right or we were wrong, but we actually have some way to measure how far we were. And I don't have it included here, but we can also sort of look at these conversations from an efficiency perspective. So we can look at the length of the conversations or the number of calls to the solver. And these give us insights into the behavior of these optimization agents. And for example, if the cost of solving the model is very high, so re-optimizing is very expensive, maybe that's something you want to penalize for, and that's something you want to track in your your aggregate score. So we operationalize this evaluation framework through a case study based on school scheduling in San Francisco, and that's because one of my advisors on this project has experience with the school scheduling problem. So we look at a simplified version of it where we just have 10 schools and 3 start times. We have an objective where we're trying to balance student load and schedule regularization. And so this is a very simple problem, but a lot of the interesting insights from this problem come from the fact that we're trying to elicit these preferences and this feedback from the stakeholders in the district. And so we look at just 4 very high-level different optimization agent designs. We consider the types of interactions they're having with the model, whether those are through tools or we allow free-form code generation. We actually consider whether or not we even give it a prompt at all. And so the idea here is that we don't give it a prompt. It's like if you were a user and you just took your query to ChatGPT and you were asking for help that way. And then we also just consider whether or not we provide solution processing for the outputs of the solver. So this just tells us whether we're returning the solver outputs in the form of raw decision variables or whether we're actually processing it for the optimization agent and returning it in the form of something that's more semantically meaningful, like a school schedule. So we have our data set of around 400 decision agents. These are based on stakeholders in the district, and these vary over their utility functions, which characterize their preferences over school start times, student load balancing, schedule regularization. And we also parameterize them by their communication style. So we distinguish between decision agents that are more vague in how they communicate and ones that are more precise. And then we also, and this is something I have not discussed thus far, we distinguish between how their check utility function is implemented. So the reason I've been calling them decision agents is because these LLM agents that are simulating humans actually have their own tool, which just allows them to query up the value, the utility value of a solution. This way, we're not relying on the LLM's own internal reasoning to calculate that based on the utility function we're providing it. So it just gives the decision agent a reliable way to calculate that utility of a solution. So just quickly going through the results here in terms of answering this question of why are conversations important. And so the idea here is that conversations reveal the true performance of an optimization agent and really gives us insight into these capabilities that would otherwise be masked under one-shot evaluation paradigms. So essentially what I'm saying is you can have a lot of ambiguity, and you can also, maybe the decision agent feedback isn't necessarily entirely specified in its initial message. As a result of that, you don't necessarily, in most cases, just through one interaction, you can't fully gauge how an optimization agent would perform over a more sustained interaction with our decision agents. And so that's reflected in both the score and the success-based metrics. And this is just for the tool-based agent here that I'm showing results for in this table. And then looking at what makes a good optimization agent, the key takeaway from this table is that tools improve the reliability for all types of decision agents. So we can disaggregate by decision agents that communicate in a vague way or a more precise way, ones that have a very simple check utility tool versus ones that have a tool that provides them with more rich information in terms of what they should look for or what they should put in the substance of their feedback. And the idea here is that, at least in the context of our case study, tools keep the optimization agent focused on very valid adjustments that lead to better outcomes for our decision agents. And so this can be an informative way of telling us how we should maybe design our optimization agents, or the optimization agent that we would ultimately want to deploy for the San Francisco Unified School District. So in terms of what we learned over the course of this talk, conversations are important because ambiguity is common and it's difficult. So being able to ask for clarification is important, and being able to understand how optimization agents handle that ambiguity and how they're able to ask for that clarification is important. And it's much easier for a decision maker to react to specific solutions than discuss abstract concepts. So you need to give these decision agents and the decision makers that they're meant to represent the opportunity to look at bad solutions, react to them, and then provide more feedback about them in order to actually make sure that they're arriving at satisfactory solutions. And then in terms of this question of what makes a good optimization agent, we know that framing the interaction around optimization is critical. So another result I haven't had time to go into here is that in the absence of a prompt, the optimization agent will attempt to rely on exhaustive enumeration rather than actually framing things around an optimization model and solving it that way. And so it's very important to actually make sure the optimization agent knows that this interaction is meant to be taking place within an optimization context. And this idea that tools make the agent more reliable at the cost of flexibility. So obviously, if you're constraining those adjustments to the model to tools, it can't do everything that a full coding agent could do. But the idea is that as long as you're careful about how you design these tools and the tools that you provide, you're not really going to sacrifice much in the way of flexibility. And you also give this optimization agent a way to frame how it's making adjustments to the model. And there's certainly many extensions here. So you could imagine giving it tools to do things like Pareto exploration, things of that nature that really expand the breadth of its capabilities and keep its reasoning very focused on these very informative adjustments to the model. So that's all I had today. I might have gone a little bit over time there, but thank you for sticking around this long.
questions, if you have any.
Yeah, thank you, Josh. So what is what the user of that tool is saying, like the end user? Because you mentioned like interaction between the decision agent and the optimization agent. But what is the like? Is this like kind of pre-filter to make sure that whatever is returned to the end user is already iterated?
So the user, there's actually no users involved in what we're showing. So the idea is you would use the decision agents for your evaluation, scoring, and then you make whatever adjustments you need in order to improve your optimization agents, and then you would ultimately deploy it. So they would never see the decision agent itself. It's meant to represent or mimic a human in order for you to iteratively improve your optimization agent before deployment. That's the idea.
So this allows you to like cut the number of times you solicitate, for example, the company you're developing the optimization for.
Sorry, can you repeat that?
Is this like to like reduce the number of time you have to solicitate the company you're developing these models for? Like if instead if like you replace the I don't know your client or like a San Francisco mayor by this like decision agent, is the goal of this to like not have to like what is the
No, the goal is just to to design the optimization agents in such a way that they give us good results in our decision agent data set, so that when we were to deploy them, so if the mayor were to come and interact with it, we know that our optimization agent would reliably help the mayor find a good solution based on how it's performed on our data set.
Yeah, great talk. So do you envision this kind of tool? I think it helps you mitigate ambiguity, right? But you can never eliminate ambiguity. So when you think of some kind of agile development environment, do you imagine this could be useful to speed up the cycle, like different versions of products?
So you're saying like a simulated environment where you can simulate this ambiguity over and over and make sure you're good at handling it before deployment is like essentially sort of what we're doing here? Or?
Yeah, because my thinking is that regardless how good job you're doing in eliciting user preference, eventually users are not going to like it, right? Once they see the product, they're going to hate it. So you're actually going to need another cycle. Is this going to be fundamentally different from the traditional agile development approach? You basically have a version 1, version 2, version 3. In between, you're getting user feedback.
I see. Yeah, so I think eventually you would reach a point where you would need to bring it back to the researchers. And you essentially, during deployment, I guess the idea would be you would gather that feedback, you would see where it's going wrong, and then you would do additional training. Maybe you would see the instances where it's going wrong. Specifically, you can design decision agents around to mimic those behaviors where you see it goes into those failure states, and then you can try to use that to iteratively deploy better models over time. But of course, like you said, you're always going to have the issue where the humans are going to be humans, right? They're going to be ambiguous. They'll be vague. They'll find ways to say something that's going to completely throw the optimization agent off. But the idea is that over time, you can develop a more representative set of decision agents that behaves more and more like the people that you're trying to, satisfy in those interactions.
Thank you, Josh. Okay, so we are done with the agenda that we had for today. So I just wanted to thank all the speakers for sharing their work, also to everyone for participating through the discussion and questions. We really appreciate you being here. And finally, we just hope that this seminar helped surface interesting directions and spark conversations across the community, especially between people coming at these problems from different perspectives. So thank you so much.